who will be giving us a talk about a project he participated in collaboration with JPL and NASA.
Hello. Good morning, everyone. My name is Kareem Elaasar. I am a master's student currently at UCI, studying software engineering, and I do have an emphasis in machine learning and AI, which I recently acquired over the past few months. And so today I will be presenting a project that I did with JPL last summer for an internship called Document Analyzer using LLM. Okay. So the problem is analyzing documents manually is difficult, right? So this problem came initially from NASA HQ, and the problem that they were facing was most of their documents or their information was stored in documents, hundreds, thousands of documents, and to be able to search for specific information in those documents, especially information that isn't exactly mentioned but could possibly be inferenced, is difficult, right? Because there's a really large volume of data, and for having an engineer to manually parse that data, it's not really reasonable. It's not really feasible. And some of these types of documents could be ConOps, interface control documents, issue reports requirements, policies, or methodologies. And like I said, one of the main problems is the overwhelming volume. A lot of the text can be ambiguous, so different people could misinterpret the same sentences. Obviously, we have limited memory and so on. So because of human limitation, it's not really feasible. So how can we solve this problem? Well, what we decided to do was split it into two initial approaches. So the first approach would be to use an LLM to analyze the document for us. So kind of sort of a RAG approach. So we would simply feed the LLM the documents or information and then just ask it questions about it. The second approach would be to create a structure for the documents and structure the documents as analyzable data sets using ontologies. So what we would do essentially is create a schema, and this part is manual, the approach too. So we would kind of create a schema of what we want to extract from the text and then manually fill in that schema through assertions from the text. And the solution would be a combination of both of these approaches, as both of these approaches individually have their own drawbacks, which I will discuss further in the presentation. And the solution would be to use an LLM to structure the documents for us as analyzable datasets. Okay, so let's talk a bit about approach one, which is use LLM to analyze documents. So again, we spoke about the manual drawbacks, which was facing an overwhelming volume of information, inconsistent language, so the same thing could be said in various ways, cognitive limitations, aka our limited memory, and so on. And so the LLM obviously is much faster than us at reading information and understanding it. And so those issues it does address. However, as a generative model, it does lead to its own drawbacks, which is, as we know, it can hallucinate and basically fabricate data that isn't really there. And this could be due to knowledge gaps or some way it kind of stores information in memory. Either way, it does have a hard time admitting when it doesn't know the answer. It's also pretty inconsistent, as its outputs are variable and probabilistic. So we're never going to get the same answer every time. And without some structure, we can't really rely on it because it's just a bit informal. Yeah. So an example of this happening is there's this document called NPR where it's just a bunch of nuclear procedural requirements, and we fed it a prompt, and the prompt read, extract nuclear safety policy roles and the relationships organized as triples so we can visualize the interactions and analyze them, detect risks, and find ways to streamline communications. And specifically mentioned, we want the triples to be in the format role, relationship, then role. So the relationship between those two roles. And so we fed it the document. So it's supposed to apply this prompt to the document and extract the triples that it could find. And if we look at number 7 here, you notice that there's actually 4 fields: chief, safety, admission, and admission assurance, designates, nuclear safety officer. So first problem is it has 4 fields when it should have 3: role, relationship, role. Second problem is you see nuclear flight safety officer, and it is a role. However, this can also be abbreviated, and it is abbreviated in the document as NFSO, and in other triples, it is shown as NFSO. And so it's kind of creating 2 different roles for the same exact thing. So that's some redundancy. And if we look at the other triple, number 8, we could see that it mentions the first role, administrator, which is a role, determines capability of, which is a relationship, and then radiological risk, which is not really a role. So clearly, without any formal structure, it doesn't really give us exactly what we want in the exact way we intended it. Now let's look at approach 2, applying structure to documents. However, this is without LLM, just manual work. So a subject matter expert can model domain vocabulary using an ontology, which is OML. Then an ontological model is created to represent what we want to extract, like we said. So individuals, roles, relationships, concepts, rules can all be extracted. And this can be facilitated by OpenCaesar, which is an open source framework for ontological modeling / analysis developed by JPL, which does give us OML and analysis tools. However, like I said, this does present the drawback of manual work. So here's an example of using this structure and filling it with manual work. So let's take this Wikipedia snippet about Thomas Jeffrey Hanks. So as we know, he's a famous actor, and in the 2 green boxes at the top are our OML ontology, our schema. So here we're outlining that we want a person and a production, so these 2 classes, and then the relationship between them is the production has an actor and it also has a director. So we're applying that to the text, and we're essentially filling those assertions from the text into an A box, or an output assertions, so the middle sector. So we can see the persons we can find in the text are Thomas Jeffrey Hanks and Steven Spielberg. And then the production, we could possibly take the terminal. Now, if we fill that in the ontology, we have person 1, which is Thomas Jeffrey Hanks, person 2, Steven Spielberg, and production 1, which is the terminal. And you can see that we linked has actor. The production has an actor of Thomas Jeffrey Hanks, and the director is Steven Spielberg. So using the ontology, we filled in what we can from the text into these assertions. And the final step would be to, once we have a bunch of these assertions, we could fill them into a knowledge graph or a database, and then we could query that database using that database's specific respective query language. So at the bottom here, we have an example of using query language to answer the question, what are the names of the productions that Tom Hanks acted in and were directed by Spielberg? Now, again, we talked about the solution earlier. Yeah, right. So we spoke about the solution earlier, and the solution was to combine those two approaches. And that's where we get the document analyzer tool, which is a combination of LLM prompting and ontological modeling. So the pipeline goes like this. First, an expert defines a structured ontology for a document. So given a document, it starts from the right here. We will want to define a schema for which we want to kind of tell the LLM which information we would like to extract from the document. So once we define that schema or that ontology, we feed it to the LLM along with a prompt instructing it to do so. And then we feed it the document as context, and the LLM should extract that specific vocabulary into a structured data set, like we showed earlier. Once that happens, the data set won't be perfect. Again, even with these techniques, LLMs will never be 100% perfect, at least for now. So an expert is going to have to curate the data set and fix some of the mistakes it made. And this can be enhanced with analytical tools from OpenCaesar. However, in this project, we did do this curation manually. And once we have a curated data set by the expert, we can then publish it to a knowledge base, which then an end user, can then query that database using a query language and extract whatever information he wants with ease. And this can also be enhanced with LLMs. So you send an LLM your natural text, and it could generate a database query on its own. And an example of this in action. So we have the prompt, read chapter 2 of NPR and extract an ontological data set based on this OML ontology. And as you can see in the top right, our ontology is role, which is the relationship is responsible for, and then responsibility, which is the second class. And we have other relationships as well that we will feed to the LLM so that it could decide how it wants to fill those in. And we fed that prompt, we fed that document on the left. And as you can see, it took certain classes such as MDAA, notifies NSFO, so it made that relationship on its own. MDA is responsible for provide resources, notify NSFO, and so on. Those are responsibilities, and it automatically filled those assertions, and it did much better than those other two approaches. And again, the last step was to query the database. So once the knowledge graph is created, so we have an example query list rules along with how they are interrelated. And that is the equivalent Sparkle query. Sparkle is the query language for GraphDB, which is the knowledge graph we used. And so future work, Definitely a lot of improvements can be made. We could definitely develop a UI to facilitate the user experience. So currently, most of it is through the command line, so it's not really as interactive. We could also possibly use different LLMs as we use GPT and it was quite expensive. And we could also research better prompting techniques to improve the LLM's accuracy. And yeah, any questions?
Thank you, Kareem. I think we have a question from Nicholas.
Yeah, actually, I'm thinking back of the presentation from Giancarlo, right, about like value and risk. And there was a quote somewhere in this presentation from Milo Punos where it said, like, if you don't know what you're looking for, you're in the dark, right? And so listening to your presentation, particularly like about the user queries, I was thinking it might actually perhaps make sense to, in addition to having kind of like the subject matter vocabulary available to structure the data, to think about, well, how do you describe some expectations and perhaps some threats about what kind of queries you expect users to be able to get useful results from this? And to address these concerns about like hallucinations and errors and things like this, to think in terms of like threats, how could you describe, again, at the level of the vocabulary, what would constitute effectively misleading data that could perhaps be, a bad query result. So I would encourage you to actually look at what Giancarlo described in this value and risk to see how some vocabulary that would be a companion to the schema that you have could help avoid or assess how well the query results are.
So basically you're saying if you can beforehand outline what could be a misconception or something wrong and outline those cases so that when you prompt, the LLM is aware already of these misconceptions and
right, because
reducing the
in the
hallucination.
example that you showed, right, was like role relationships, but what's a role? So how do you know that in fact you've recognized a role properly?
Yeah.
So again, like having some kind of like a schema to say, well, a role needs to have a certain pattern in the data to say it's a role.
Mm-hmm.
That would be like a criteria to filter out things that are role versus things that look like role but are not.
Right.
Again, like what's the role relationship? Again, there's certain kinds of things that perhaps people expect, some things that you don't want to include as role relationships, even though they may appear to be.
Right. Great. Thank you very much, Kareem.
Thank you.